Let's create a reinforcement learning environment in Unity that we can control from Python. So this means that from Python, we can take a step, we get a reward, and we get an observation. We can also reset the environment and get another observation. This tutorial builds on the previous tutorial, which is the simple networking, the Python controls Unity tutorial. So it assumes that you have the knowledge from that tutorial, like you know how to create RPC calls from Python into Unity, and it's going to start exactly where that left off. The scenario that I think would be fun to do would be to have an agent just chasing a target. The target's not actually going to move for now. In some later video, we'll make it move. And the agent is going to be the sphere. Let's go to the first task. The first task is called agent appears. And we're just going to start off simply. So let's just rename the sphere to agent. Here I've got where we left off. So we're just going to rename this to agent. And then if we go into so I'm using Visual Studio, the same as before. I mean, Visual Studio Code, but obviously you can use whatever your preferred editor is. Going to rename the script to agent and rename the class. We also have to do bit more renaming actually, because this is expecting sphere. So I'm going to use search and replace. I'm going to go from sphere to agent. I'm going to make this preserve case and replace all, and there we go. All right, and that should compile hopefully. There we go. But if we look down here, it says missing script. So we basically need to remove that and then re-add the agent script into the agent. Did I add it? Yes, so that's good. I guess we can just check that runs. I mean, it should run. And I guess we can try calling it from the Python. So we can do like get pods. All right, there we go. So that's working. All right, so have we renamed the game object, the script, and the class from sphere to agent? Yes. So let's go to the next task. All right, so the next task is called agent move. This task is a little bit longer. In this task, we're going to add a step method that we can call from Python. We're going to have 4 actions, so north, south, east, or west. So north and south should move along the z-axis. East and west should move along the x-axis. And these are non-physics moves. We'll have a move speed of 10, and the delta time will be time.fixed delta time. And then we need to create a step.py Python script to test this method. We need to first create a step method in the RPC class, and we'll have a step method in the agent class, and the step method in the RPC should call the step method in the agent. So I'm going to go into the C# code, and first in the RPC, we're going to create a method called, we'll annotate with the json-rpc method. We'll call it step. It doesn't have any return value, and it's going to take in a string, which we're going to call action. It doesn't have to be a string, could be an int. I originally did it with an int, but like, I think action, having it as a string is maybe more interesting. I don't know. Anyway, so then we're going to call agent.step with the action, and then we need to create the step method. So let's get rid of that and this, oops, but not get rid of this curly bracket, and then public void step, and then string action. And then here, so I'm using Python 3.10, so I'm going to do match on, oops. Oh, I didn't want to see switch. Switch action, and then case, and then we've got north, and then south, east, west. So south, east, west, and then we're going to have a direction. So let's create a vector direction, and we'll just set it to like vector 3.0, so it's initialized. And then basically at the end here, we're going to do like transform dot position plus equal direction times the speed, which is 20, times time dot fixed delta time. Right, and then we need to get the direction. So if we're going north, then the direction is vector 3 dot forward. And if we're going south, it's going to be minus vector 3 dot forward. Let's stick in a break. I guess we can stick breaks for all of them. And then if we're going east, we can use vector 3.right. And if we're going, so plus vector 3.right, and if we're going west, we can use minus vector 3.right. All right, so I think that should be the C#. Let's just check that compiles. All right, that's compiling, and then so before we run it, let's like change this around a bit. So wait, am I running it? No. No, I'm not. All right, so let's have Z going outwards and X going to the right. And let's just like pull back slightly. Let's get rid of this directional light. So we can get rid of that by putting it to -50 because it doesn't actually depend on the position. It will work just as well no matter where it is. So the lighting didn't change. And that way it's out of our view. And then let's take this camera and we'll do align with view. And so now, like in the game, it's the same viewpoint, right? So we're looking from above, basically. And then let's press play. And then, oh, we have to change the step, right? So the moment, oh, we don't have a step. Right, so we're going to take the translate and we'll rename that to step.py, keyboard, step.py. Here we'll do unity_const.step, and then we're going to do action equal args.action. We can get rid of this translate, and then we need to have an action down here. So the action is going to be type of float. We can either make it required true or give it choices. I'm just going to set required equal true. Giving choices would probably be cleaner. All right, and then we got step and then minus action north. And then let's have a look at our display. So yes, okay, cool. And then east, and then south, and then west. All right, so if we go look at the task, do we have a step action that takes in a string, goes north, south, east, and west? Yes. Do we have are we multiplying by the speed 10 and the time fixed start to time? Yes. Well, let's just like go there. That's this bit. Oh, whoops, that should be 10, right? And we have a step.py script to test that. All right, so let's look at the next task. So the next task is called to trap the agent. And basically we want the agent to stay within a small area so that when we're actually training on this, the agent's not just going to let it run off to infinity. It's just going to stay within the square. And that way it has a realistic chance that it's going to be going to by chance run into the target. So restrict the agent to stay within x -3 to 3, y is 0, and z -3 to 3. We should use test.py to step this. We can use mathf.clamp to clamp a number into a range. So we can't actually clamp the position here. Now if we do x equal like mathf.clamp, that's not going to work. It's not going to like that because you can't assign to the individual elements of that won't work. Right, cannot modify the return value of transform position because it is not a variable. Right, so what we can do is, instead of directly assigning this, what we're going to do is we're going to create a new vector 3 called like for example new pos, and we're going to set that to our position plus this change in position. And then here we're going to do transform.position equal new pos. And then here when we do the clamp, we can do new pos dot x equal mathf dot clamp. We're going to clamp the x and we're going to clamp the z. We don't need to clamp the y, but I guess we could just do new pos dot y equals 0 just for completeness because that's in the task, right? All right, so that should work, and then we can test that. So let's stop that and then start it. And then we can call, so let's like, I guess we can kind of like drag this across to like x is -2.8 or something, 2.95. And then if we do west, and then it stays at -3. If I drag it further, it comes back. If I drag it over to the right, it's going to come back. If I drag it north, so this is like z is 3.61, comes back. And if I drag it, oops, oh, I can probably test the y clamp too. All right, so we've got y is -8 and z is -10, and now it's come back to y equals 0, z -3.
Wait, why isn't the agent moving? Is there a bug? Who are you to tell me what to do? You keep telling me to move north, east, west, south. Why should I listen to you? You're doing a great job, agent. Yeah, I know. I appreciate what you're doing. Thanks. Can you move west now, please? Fine. All right, so it looks like the agent's moving now. So yeah, thank you, agent. Appreciate what you're doing. All right, so let's check the task that we just did. Have we restricted the agent to stay within these bounds? Yes. And we used step.py to test this, so that's good. All right, let's look at the next task. So the next task is called target enters, and we're going to create a target. Just need to create a target object. Should be on y equals 0, otherwise they won't collide with the agent later. Should be about size 1. I'm just going to make the target a red default cube. So we're simply going to, in Unity, I'm just going to create a cube, and I'm going to make it red. So let's just move it away from the sphere. To make it red, we're going to add a material. So in the assets folder, I'm going to create a folder called materials. And then inside that, I'm going to create a material called like red mat. And I can drag that onto the cube, and I can change the color here. All right, so we've got our target, and we need to rename it to target. All right, so we've got target. Yeah, let's save. All right, so have we created a target object on y equals 0? Let's check the y. Yeah, y equals 0, so that's good. And it's about size 1. We can see that in the scale. All right, okay, cool. All right, let's go on to the next task. The next task is called reset. And what we need to do in this task is to add a reset method that we can call from Python. It should move the agent to 0, 0, 0, and it should move the target to a random position in the range, like x is -3 to +3, z is -3 to +3, and y equals 0. It should not overlap with the agent. And we need to create a reset.py Python script to test this. If we add a game object reference to agent, then we can move the target from the agent. We don't need to add any script into the target object. We can create random numbers using random.range, min and max. One gotcha here is that if you give integers for the minimum and maximum, you will get integers out. That they will be as type float, but they will be like -1.0, -2.0. They won't be like -1.23 or something like that. If you give floats, it will become actual floats like -2.3 or something like that. And for the overlap, we can simply try different target locations until we find the one that is not overlapping. So in the C# code, we're going to have method reset. It doesn't have any parameters. And we'll also add that into the RPC class. So here we'll have a method called reset. It doesn't have any parameters, and it's simply going to call agent.reset. So we can do the easy bit first, which is simply setting our own position to 0. So we can do transform.position equal vector3.0. And then we need to think about the target location. So the first thing we need to do is get the reference to the target. So if we go up here, we can create a reference. We can do public game object target, and then we can assign that in the Unity editor. So if we go to the sphere, and here we can choose the target. So now we can assume, let's save that. And so now we can assume in the script that this is set to be the target game object. If it's not, we'll get an error. Okay, so now what we can do is we can set the position of the target here by doing target.gameObject.transform.position equal some position. So then we need to get that position. So for the overlap, like we want to try different positions until we find one that doesn't overlap with the agent. So I feel like one way to do that is to first set our new position to be the position of the agent. And then we're going to have a loop that as long as the target is too close to the agent, it's going to generate a new position. So we can do vector3 new pos equal like our own position. And then we can do new pos minus our own position, and we can do dot magnitude. So then that's the distance between the agent and the target. And as long as it's less than say 1.5, then let's generate a new position. So to generate the new position, we can do new vector3 And we're going to use random.range -3 to 3, but we have to be careful to use floats, because if we use integers, it's going to return integers. All right, and then random.range. So for the y, we're setting it to 0, and then for the x and z, we're setting it to random.range. And and then we have to apply it here. So that should basically be it, I think. So let's check this compiles, and then let's try running that. And then we just need to create the Python script. So it looks like they're compiled. Here it is running. And then let's create the Python script. So let's just copy and paste the step. And here, instead of calling step, we're going to call reset. It doesn't have any parameters. It doesn't have any return. We'll add some return later for the observation. All right, there we go. All right, so let's try calling that. So if I call reset, all right, so the agent is now at 0, 0, 0, and the target is within the bounds. And each time we do it, the agent stays in the same place in the center, and then the target's moving. So that seems good. And the target's never overlapping with the agent, which is good. All right, so have we achieved the task of creating a reset method that we can call from Python? Yes. Does it move the agent to 0, 0, 0? Yes. Does it move the target to a random position within this range? Yes. And does it avoid overlapping agent? Yes. And we created a reset.py script to test this. Let's look at the next task. So the next task is called collision detect. So in this task, we need to detect when the agent collides with the target and log win to the console. So there's a few hints for this one. So one body and exactly one body should be a rigid body. Since we're not using physics, then we need to set that body to kinematic. Exactly one body should have collider set to trigger. And we should use, well, we can use on trigger detect to detect the collision given the thing above. It's possible to have more than one body being rigid body kinematic and more than one body with trigger, but we need to modify options in physics if we do that. And we should make sure that the y of both values are set to 0, otherwise they won't collide. So now what we're going to do is we're going to make the agent rigid body. So we're going to add component, physics, and rigid body. And we'll set that to kinematic. And then in the target, we don't need to add a rigid body, but we have a collider and we need to set that to isTrigger. And then let's save that. Okay, and then in the code, so we only need to detect the collision in one of these scripts, and we'll detect it in the agent. That way we don't need to have a target script. And all we need to do is create an on trigger enter method, and that's going to take a collider. Now, since there's only these two objects, we don't actually need to check what the other collider is. So we can simply do debug.log win. All right, and then let's check that compiles. So that compiles, so let's run that. And then let's try, well, let's move the agent near to the target. And then let's call like step a few times with west. Wait, why is it going that way? Oh yeah, there we go. Oh, because I've already changed its where at. And there we go, win. So that's working. All right, so have we achieved the objective of logging win to the console when the agent collides with the target? Yes, we have. All right, so let's look at the next task. So the next task is called bouncing ball. Now this has nothing to do with creating the reinforcement learning environment, but what it does is it lets us see time, visualize time, because up till now, the agent only moves when we call step, but does that mean that time is frozen between our calls of step? Or could it be that time is actually moving? We just don't see it because nothing's happening. So with the bouncing ball, we'll be able to see time because we'll be able to see if time is frozen, then the ball will stop. And if it's not frozen, then the ball will keep bouncing. So the task here is to create a perpetual bouncing ball with perfect elastic collisions. Should be outside of the play area. So like beyond x is -4 or 4, and beyond z -4, 4. Let's call the bouncing ball ball. So the hints are, so we can use a single cube as a platform and then place a new sphere a few units above it. We can create a new physics material with bounciness set to 1, and then we need to add that to both the platform and the ball. We need to make sure to add a rigid body to the bouncing ball, and we should add constraints on the X and the Z position so it doesn't fall off the platform. So we can create a cube, which is going to be our platform. And I guess we can call that platform. And then we'll stick it to like I guess X is 4 is fine. And then we'll create another 3D object, which will make it a sphere. And we're going to call this one ball. And we'll drag that over to the cube, and then we can drag on the Y to move it up a little. And then we'll add to that a physics rigid body. And this is not going to be kinematic, so it's actually going to fall because of gravity. And let's just, if we go to constraints, we can stop it rotating, and we can constrain the X and the Z. Now, if we do that, it will fall, but it won't bounce. So what we do next is let's create a physics material with perfect bounciness. So we'll create a folder. We'll go to assets. We'll create a folder called, let's say, PhysMap. And let's go inside that folder. And here we're going to create a physics material, and we'll give that perfect bounciness. So let's call that bounce. See? And over here on the right hand side, we've got bounciness, and we'll just set that to 1. So if it's 1, that's perfectly bouncy. And we'll drag that onto both the cube and the sphere. And then now, if we play it, it bounces. And it'll just keep bouncing because there's no air resistance, and it's perfectly bouncy. All right, now notice that we're not calling step and it's bouncing. So obviously time is not frozen. And I mean, I can call step, but the ball, it doesn't change how the ball's bouncing. It's not frozen in between. So for the reinforcement learning, we do actually want to freeze time between calls to step. During the step, we want to have an action, and then we're going to return the reward from taking the action. So we want time to move then, but the rest of the time, we want time to be frozen. You've probably guessed that the next task is going to handle that. So that's true. So the next task is called simulation, and we're going to add a simulation component to the agent from the Peaceful-Pi plugin. And what that's going to do is that's going to freeze time. But it's also going to stop collision detection. But hey, one step at a time. If we go into plugins and we open up the Peaceful-Pi, then we have these scripts. And all we need to do is drag simulation into agent. And we can see simulation over here. So it's got a simulation step size, which is pretty important. So this is the size of each simulation step in game time. It might not correspond to real time. And in fact, we're going to reduce the real time to accelerate the game, to accelerate the training. The real step time is partially determined by the real step size. Real step size is going to set the time dot fixed delta time. Simulation step size is going to set the size of the steps in game time. All right, now if we play this, we'll see that the ball doesn't move anymore. So we've frozen time, but on the other hand, when we step, the ball still doesn't move. So we're not changing time when we do step. And then when we actually collide, let's show the console. There's no actual collision, so the collisions are disabled now. And the reason for that is because we've shut down physics, like we've paused physics. And in order for the ball to move, we need to step the physics. We need to call physics.simulate or simulation.Simulate. And we're going to use simulation.Simulate. Also, the collisions won't work until we call physics.simulate or collisions or simulation.Simulate. Now, we're going to use simulation.Simulate. The reason is that simulation will also handle not just the physics stepping, but it will also handle objects that have update methods and fixed update methods, and we'll see that later. Not in this particular video, but we will see that in a later video. So the next task is to add a call to simulation.Simulate into the step, so that when we run the step, it is going to step time. The ball will move full slightly, collisions will work. In the C#, in the step, so after making the move, we can call simulation.Simulate, although we can't do that just yet because we don't have the simulation object. So let's go and do that. So up here, around about where we've got the RPC, we can also create a simulation object, but we need to get hold of that object. Right now, it's just a variable that points to nowhere. And we can do that using get component. So we're going to do simulation equal get component, and it's in the same object. So we can simply do get component. Here we're going to put simulation, and now the simulation variable points to the simulation. So that should be it. So let's try compiling that and try running that. So now we're running it, and now the ball is still frozen, but when we call step, the ball should move a little. When it's right at the top, it doesn't move very fast, but you can see that as it starts to fall, it's gradually gaining speed. And while then that's going quite fast. And meanwhile, when the agent hits the target, we should get a collision now. All right, we get our collision. All right, so we've fixed physics. So now physics is frozen except when we call step, and then we unfreeze it briefly. Cool. So we called simulation.Simulate inside the step to re-enable the collision. All right, so now let's look at the next task. So simulation.SimulationStepSize. Yeah, okay, so it's not obvious, but the movements are smaller than before. It's hard to compare because if I remove the... Actually, can we compare? I guess I can just remove this. What happens if I remove this? I'm not sure. So let's remove that and then try again. And so it moves a lot more now. So let's add back in the simulation. Now the reason it moves a lot less after we've added the simulation is because we are using time.fixedDeltaTime. The simulation modifies time.fixedDeltaTime in order to accelerate training. What this means is we should use simulation.SimulationStepSize instead of time.fixedDeltaTime in our scripts, and that will fix the issue. More detail is that Unity more or less runs single-threaded. There's a single event loop. When we call the Unity API, we must call it from the main thread, in other words, from the event loop. Our networking layer, therefore, needs to run in the main thread somehow, meaning it has to hook into the event loop. And how to hook into the event loop? Two main ways to hook into the Unity event loop. One is update and one is fixed update. Peaceful Pi hooks into fixed update. Now, by default, fixed delta time is set to 0.02 seconds, which is 50 frames per second. So that means that the maximum number of network requests the Peaceful Pi would be able to handle by default would be 50 requests per second. There is a way to get more than 50 requests per second, even if we hook into fixed update, if we simply lock the editor. However, I rather like being able to use the editor while I'm training and being able to look at the properties of objects. An alternative option is to simply reduce the fixed delta time. So if we reduce the fixed delta time, we can get more requests per second than 50 and without locking the editor. We don't have to do that. We could keep the fixed delta time to being 0.02 and then we can train, but we'll have to train at real time. If we allow ourselves to modify the fixed delta time, then now we can go faster than 50 requests per second and the editor won't be locked. We can still continue to use the editor. But we have one trade-off that we need to make if we do this. We can no longer use the fixed delta time when we're updating positions in our scripts. We should multiply by simulation.SimulationStepSize. All right, so that's the task. We need to migrate step from time.fixedDeltaTime to simulation.SimulationStepSize. Very simply, all I need to do here is we already have the simulation object, so I just need to replace the fixed delta time with the simulation.SimulationStepSize. Now, if we rerun this, the size of each movement should be comparable to how it was before. So now it moves further each time. So that's great. And yeah, the collisions still work. All right, so have we migrated step from time.fixedDeltaTime to simulation.SimulationStepSize? Yes. All right, now let's look at the next task. So the next task is called reward. And what we need to do here is return a reward from step. So at the moment, we're calling step with an action, but we're not getting a reward. The reward should be 1 if the agent collides with the target in that step. Otherwise, it should be 0. And we should upgrade step.py to display the reward. We can create a variable reward. We'll set it to 0 at the start of the step. Now in the step, we're then calling simulate. So then if we return the reward at the end of the step, then we will have taken account of anything that happened during that simulate step. We can increment the reward in onTriggerEnter. That onTriggerEnter will run during the simulate, and therefore by the end of our step function, the reward will have incremented if we collided. In the agent.cs, we're going to create a new variable of type float, and we're just going to call it reward. We don't really need to set it to 0 anywhere like reset. We just need to set it to 0 at the start of the step. So in the step, we'll do reward equals 0. And then at the end of the step, we're going to return the reward. And so we'll make this a float. And in the RPC, we'll also make this a float. And we'll make it return. Now we also need to have the reward when the collision occurs. So if we go down to onTriggerEnter, all we need to do is reward plus equal 1. And that's enough. So we're setting reward to 0 here. When the simulate runs, if there's a collision, that will increment reward by 1. And then when we return the reward, it will be 1 if we collided. And now we can compile that and run that, check that that compiles and then run that. All right. And let's move this a little bit closer. And then let's take a few, oh, right. We need to, did we implement in the Python? I don't think we did. All right, so let's implement in the Python. So we're going to step, and then here we're going to do res equal, and then we can print the res. All right, so now when we call the step, we're getting 0 because there was no reward, and then now we should get 1. All right, so we've implemented the reward. We get a reward of 1 when we collide with the target, otherwise we get 0. So we finished this task. And so let's go on to the next task. So the next task is called episode finished. The task is to upgrade step to return whether the episode is finished. And the agent should finish when the agent collides with the target, and it should stay finished until we call reset. We should make sure that the step.py displays both the finished and the reward, and we should run the step.py to check it works correctly. So because we need to return both the reward and the finished, but the function can only return one single thing. So what we can do is we can create a new class called RL results that contains the finished and the reward, and we can return that from the step. And it's totally fine to return that all the way through the RPC to the Python side. On the Python side, we can simply print that as a dictionary, but we could also use the parameter result class equals when we call step to specify the return object class. Should be a data class. And then if that class structure matches what we're sending from the C# side, then the Python will convert the dictionary into that object through the magic of Chili library. And then we will print the object. If we go into the agent class, let's create a variable called finished. It's going to be a Boolean. We'll set it to false in the reset, and we'll set it to true in the onTriggerEnter. we will create a class called RL result, and let's make that public. And let's also make the myVector3 public. I don't think they actually have to be public because the myVector3 doesn't have to, but they have to match, and maybe it's easiest just to make them public. All right, this should have, these definitely need to be public. These properties need to be public. So we're going to have a float reward and a Boolean finish. If we don't make these properties public, the Python side will just get back like an empty dictionary. It's kind of confusing. All right, and then let's make a constructor that will populate these. So it's going to take in a reward and finished. And then we're simply going to do like this dot reward equal reward and this dot finished equal finished. All right, so then we can take this RL result, and in the step, instead of returning the reward, we can return a new RL result. And then here we can simply put like reward and finished. Then we need to change the return type of the step to RL result. And if we go into the RPC method, we also change that to RL result. Now this should compile and run, and it should do what we want, I think. And then we'll just look at upgrading the Python side so that it converts the dictionary into a data class object. So if I run step.py and like, I don't know, like west, let's say. So now we're getting back the finished is false. We're getting back the finished value as well as the reward. And then if we keep going until we hit the red thing, the target, then the finished becomes true, and it will stay true. We're not getting any more reward because the on trigger entry is only firing once. It's not a continuous trigger, and the finished will stay true until we call reset. When we call reset, we won't see if the finished is now false, but if we call step again, we can see that it's false. All right, so we have upgraded the step to return whether the episode is finished. It finishes when the agent closes for the target. It stays finished until reset, and the step.py displays both the finished and the reward. But let's upgrade the step.py to convert that dictionary into an actual like object. So I'm going to make a data class on the Python side called RL result, and this should be a data class. It won't work if it's not a data class. It will work if it is, hopefully. We'll have reward, which is a float, and we'll have finished, which is a Boolean. Let's just spell float somewhat correctly. Then what we need to do is in the step, we need to add in a parameter result class equals, and then this is going to be the class that the method's returning on the C# side. So we're just going to put RL result. Basically, this just needs to match the structure. The structure of this class needs to match the structure of what the C# is returning. All right, now if we run that, this is already the Unity side is already running, and now we get back an object like an RL result object with result 0 and finished false. Okay. All right, so we've completed the episode finish task, so let's look at the next task. So the next task is called observations, and we're going to give the agent the ability to see, or at least to perceive the world sufficiently to be able to achieve its task. What we're going to do is to upgrade step to return an observation. Reset should also return an observation, and let's make the observation simply the vector from the agent to the target. Let's just keep it really simple. And the step.py and the reset.py should both print the observation. If we go into the C# code, if we go into the agent, let's create a method called getObservation, and it's going to return a myVector3. And this is just going to be the vector from ourselves, from the agent to the target. So if we do like target.transform.position, and we can subtract our own position from that, and that gets us the vector from us to the target. We need to convert that into a myVector3. So we'll do myVector3, and so that because the myVector3 can be sent across the link between the Python and the Unity, whereas the vector3 can't be. All right, so we've got our get observation. Now we can simply slot this into different places. So in the reset, let's make the reset return an observation. So we simply do return get observation. We need to change this to be a myVector3. And we'll also need to change the RPC method, wherever that is, here, right? So this will be a myVector3 and we'll return it. So that's the reset reset now returns an observation. And let's do the same thing for the step. So the step's returning an RL result. So what we need to do is to modify the RL result to be able to contain the observation. So we'll add in an obs property, and we'll add into the constructor a slot for receiving the observation, and then just do this.obs equal obs. And now all we need to do is modify the step. When we create the RL result, we simply need to at the end call get observation. All right, so I think that should be the C# side done and working. So we can compile, that should compile, and we can run that. Now we can run the Python side, but it won't print the observation. But let's just show that we can run it and it doesn't print the observation. So we get back an object, and it's coming back as an RL result. Now it's actually, the observation is actually being returned. It's simply that when we're declaring the data class, we're not declaring that observation. All we need to do, if we want to have the observation available, is add into the RL result class obs myVector3. That's all we need to do. Once we've done that, now we should get back the observation too. And then if we look at this, we've got x equal minus 2.06, and then each time we call it, then the x changes by about 0.2 or so. All right, and then we also need to add the observation to the reset. So we can just do res equal and then print the res, but that will be a dictionary, but we want it to be a myVector3. So in the same way as for the step, we can do result class equal, and then, but now it's going to be myVector3. So now if I call reset, yay, I've escaped. Finally, I'm out of the game. I'm so tired of being told to reset and reset and reset, and now I'm outside the game and you're inside the game.
Oh my god, I'm trapped in the game.
What? Yes, you're trapped in the game. Okay, you guys out there, I'll see you next time, and I'm gonna build a reinforcement learning to control that guy.